Hello, my name is Cole Malenich, and this is Physics 2 Lab 5, Magnetic Braking with Faraday. To introduce the topic at hand, the objectives of this experiment were to observe a bar magnet falling through an aluminum tube and create a computational model of this scenario using Faraday's law. The fundamental physics principles used were Faraday's law as well as magnetic dipoles. The results of the experiment were as follows. The bar magnet took an average of 0.65 seconds to fall through the aluminum tube in the experiment, as opposed to 0.61 seconds in the computational model. Okay, so here are the fundamental physics principles being used in this lab. The first of these is Faraday's law, which states that the closed integral of the electric field dotted with dl is equal to the derivative of magnetic flux across an area. In this scenario, the flux is changing with respect to time because the bar magnet experiences different magnetic field strengths as it moves through the tube. Another physics principle at hand is magnetic dipoles. The bar magnet used in the experiment is actually a dipole, and the magnetic field that is induced upon it depends on the magnetic field that it applies to the aluminum tube it is being dropped through. So let's get into the experiment. These are the initial conditions. The system is the tube with the bar magnet inside, while the surroundings are everything else in the universe. As for errors, the frame rate of the camera didn't really allow for much accuracy in the timestamps, which could have accounted for discrepancy in data, but you can basically see the setup of the experiment on the right. All you do is just drop a bar magnet through an aluminum foil tube with the north end facing up and catch it when it falls through to the other side. These were the results from the experiment. We did 5 trials to obtain an average fall time of 0.65 seconds through the tube, moment of entrance to moment of exit. The next step in this lab was to computationally model the experiment using GlowScript. So here you can see I set up my initial conditions, the length of the tube, the thickness of the foil, the inner radius of the tube, and the outer radius. And then down here we have the mass of the bar magnet alongside the value of mu mag. All of these values were important to ensure that the model modeled what occurred in real life. Next up was to set up some functions. So you can see the first one gives you the magnetic field of the bar magnet, and then the second one gives you flux. And then we have some more functions. The top half is kind of for the current moving through the ring, that is the cross section of the tube aligned with the bar magnet as it falls. The bottom half of this code models the induced magnetic field at the ring. Putting our finishing touches on the model, we have the net force equation, a couple of formulas to denote the magnet's velocity and position, and the creation of a plot. This is what the code looks like when you run it. Up top, we have our visualization, and then our velocity versus time graph. The magnet looks to accelerate in the negative direction for the first sixth of the tube, then falls at constant speed for 2/3 of the tube, and finally accelerates coming out of the final section of the tube. All in all, the time in the tube was found to be 0.61 seconds. So the only thing that I could think of as a source of error for the computational model is that the value I used for mu mag was mainly so that the time could match the experimental time. Who knows if it was right or not, but it does match the experiment pretty well. So what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The magnet would fall even slower than before because less resistance equals greater current, which equals greater magnetic field or force. And then what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The current would decrease, which would decrease the magnetic field or force, causing the magnet to fall faster. That is Physics 2 Lab 5. Thank you very much.